Today we're starting on actual intersecting families, and the idea is a very natural notion. You have a bunch of sets. Intersecting just means any two of them intersect. So A living in half set of X. Remember, as always, X means 1 up to n. It's intersecting if any two sets meet. X intersect Y isn't empty, or X and Y. Okay, and if you want, you could draw the world. Here's my world X, which is a bunch of sets. And remember, the orange and red are visible, so a bunch of sets. No, it's more like some messy data that we meet. And the question is, how many can you have? Okay, that's always in extremal set theory. You always have a bunch of sets. Extremal always means how many we have few. So that's a very natural question. How many can we have? How big? Can we do? So out of all the 2 to the n subsets that you have, well, obviously, you aren't allowed a set and its complement. Right? There's no identity set. So there's a trivial upper bound of half. So at most, 2 to the n minus 1, because of x and x complement. They can't both be in the family. But equally obviously, you can achieve half, just take all sets around 1, right? 2 to the n minus 1, because that's all subsets of 2 up to n. So that's 2 to the n minus 1 can be done. For example, the set of all x such that 1 belongs to x. So that's not the end of today's lecture. By the way, there are many other examples, apart from just fix an element. You could suppose n is odd. You could take everything upstairs, couldn't you? All sets of size above a half, strictly above a half. Each of those meet for size reasons, and that's their different there. Actually, there are millions of examples. There are millions of examples. All right. Okay, so that was a pretty boring question. What if we restrict to a level? What is a family of R sets? So what if A lives in XR? This is again very, very natural in extremal set theory. We always have a question about all sets. Like, how is there a question on a level, like Kruskal's Katona for upper and lower shadow? Okay, what can we do there? Now, I guess there's some silly cases, right? Like, if you're living in a level above halfway, the answer is take the whole level. So if R is bigger than n over 2, that is silly. You can make everything. And actually, there's another silly case. If you're exactly on the middle, suppose n is even and R is half n. So if R equals n over 2, now, of course, it's not true A2 half-size sets meet, right? Because the sets complement don't meet. But that's the only way not to meet, right? If I have 2 4 sets of 8, they meet unless one's opposite of the other. So all you would do is, you would take from each complementary pair 1 set, that would be maximum. You can never have both of a pair, but you can have one of each pair. So this would give you a half of all sets. All right, so those are some silly cases. So let's be looking at the world when R is less than n over 2. So I won't keep saying that, that will always be the case. What could we do? Well, the obvious guess is, you could say, oh, I'll just take a bit over 1, like that before. Could try the set of all x, all R sets, such that 1 belongs to x. And how big is that? I guess if you're taking an R set and you fix 1 point, you have R minus 1 points to pick from the remaining n minus 1. So that has size n minus 1, choose R. That's quite a nice example. By the way, as a fraction of all R sets, that is R over n of the world. And I'm assuming you are grown-ups, not children. So I don't want you to think this is true because write down the disgusting factorial formula for this, compare it with that, and spot an R and N. What you should think is, if I give you a random R points, what's the chance element 1 is it? Obviously R with N. Therefore it's R with N. So you're not supposed to be thinking of this as write down factorials. It's going to think it's obvious because a random R set, chance element 1 is in it, it's R and N. Anyway, think the other way, that's also fine, of course. Good. There are things you could try. There are things you could do. You could say, we made this family intersecting having 1 point that guaranteed it. You could be a little less, no, you could say, what about having, say, 2 out of some 3 points? You could also try. Or the set of all x in x to the r, such that, say, x intersect square brackets 3 is at least 2. That makes sense. So it's all sets with at least 2 of 1, 2, and 3 of them. Again, that's truly intersecting family. It's not the same as that one. It's not contained in that one. So that's not quite extra thing. And similar things as well, of course. Let's just compare those. Say in, I don't know, 8, 3. So the question is, I've got some triples from 8. Which one is bigger? Let's have a look. Orange is also visible, basically. So this one, this family here, well, we know it's either 7 choose 2, which is 7 times 6, so 2, I think it's 21. How about this one? So out of my 8 points, I guess we have to have at least 2 of the first 3. We could have all of them without 2 of them. If we have all of them, if I have all those 3 points, that's 1 3 set. So 1 plus. If I have 2 of them, then I'm picking 2 from here, 1 from here. There are 3 ways to pick from here, pair. There are 5 ways to pick singleton from there. 1 plus 3 times 5 is 16. Oh, it's less than 21. And if you experiment a bit, you'll actually find that whenever you write down this form, this one always seems to win. And that's a very nice theorem. That's called the Erdos-Ko-Rado theorem. It says the biggest intersecting family is exactly that family there. That's fantastic. Yeah. So here, it's Erdos-Ko-Rado. If A that is effectively R is intersecting, then the size value at most n minus 1, which is 1. So it's saying, if R is a bit below half n, you get about half all sets. If R was a third of n, a third of all R sets, and so on. Okay, so how do you prove this? So this is a sort of general feature that I could also have talked about yesterday, I won't mention it now. Because it's kind of just combinatorics, and it's just a family of sets. There's no structure around, right? So it's never clear how it's going to start. You can't pick a basis to the vector space around. You can't say given epsilon greater than 0, then no analysis around. So it's not clear how you start. I'll show you 2 very nice proofs. Each illustrates some very good educational points. But each one is kind of, might be hard to think of if you've been else already. So I'll make them here quite natural, but then you at least think about this question for a year and not solve it. Okay, so proof number 1 would go as follows. It would say, we're dealing with intersecting families, which we don't know much about, we've nothing to talk about them. But we're experts on lots of things from yesterday. We know about things like upper shadow and lower shadow. Yeah, containment. If I told you I've got a family of sets of size 5, how few families of size 6 can contain them? That'd be upwards for Katona and Imre. So can we rephrase intersecting in terms of some kind of containment. Let's think about it. If I tell you that x intersect y is non-empty, that says that x doesn't live in y complement, right? So that's the same as saying that x is not contained in y complement. It's contained in y complement, it's disjoint y definition. So let's try and draw a little picture. Here's the cube. There's level R. That was the complements live up in level n minus R, which is the same size. So I tried my terrible drawing, is the same size block. And remember, this whole true, we're always assuming R is less than half n, remember. So that's a value picture. So here's what we're saying. Here is A. Let me write, let's say, A bar, the set of complements. So up here is what I might call A bar. So I'll write A bar for a set of all y complement y in A. So what does it mean to say that one of these is never contained in that? It says if you add elements to one of these, I guess n minus 2r times, you never land in there. Does that make sense? But you cannot take a set in here and add elements to get a set in there. That's what that says. So that says the upper shadow iterated n minus 2r times, lands up disjoint from A bar. We try going orange. So this orange thing here is where that's it. This orange thing here is the upper shadow iterated n minus 2r times of A. That making sense? So you take A, you take its upper shadow once, you take its upper shadow twice, and so on. And where you end up is disjoint from A. There you are. Okay. But not experts in knowing how upper shadows grow, right? We know the best is always a let intersecting. So, let's see what we get. So suppose for a contradiction that the size of A is strictly bigger than n minus 1 choose r minus 1. And so, of course, the size of A bar is also bigger, they're the same, right? So the size of A bar is also bigger than n minus 1 bar. Okay. Now, what are the first n minus 1 choose r minus 1 things in X? They are everything contained in the 1. Right? Remember that Lex is defined out, so it's a nice case of Lex, like the kind of thing I did with you yesterday, 3 sets from 9, rather than unpleasantly with a low shadow. So it's a nice case, right? Everything with a 1 is the winning set for Lex, right, for upper shadow. And again, this isn't the size of everything containing 1 by luck. It's because, of course, the family we're comparing it with is exactly what things with the 1, so no surprise there. Okay, so what do we know? The size of A is at least the size of all the R sets for the 1. So that's best the upper shadow. Now what's the upper shadow once? What is the upper shadow, like all supersets of everything with 1? It's of course all R plus 1 sets with a 1. Agreed? If you take a set with a 1, add an element, choose that with a 1, and conversely, if I give you an R plus 1 set with a 1, you can, by clever calculation, think of an R set, if you add an element until you get to it. Right. So this thing is everything with a 1, and therefore so is that thing. I'll show you again. So I keep applying KK upwards. I deduce the following. So the size of the upper shadow iterated n minus 2r times of A is at least the size of all the n minus r sets with a 1. That make sense? So what do we have living up here? I've got an orange thing, which is as big or bigger than all the sets from the 1 at that level. I've got a red thing, all the complements. How big is that? Well, no need to fiddle with the coefficients. Remember, this number here is all our sets with a 1. Take their complements, don't get exactly all n minus r without a 1. So the size of the red thing, a bar, equals the number of n minus r sets without a 1. Either because it equals n minus 1 to something, or the equal complements. So, and the size of a bar is strictly bigger than the size of all n minus r sets without a 1. But that's conjecture, right? That said, I've got living in this level 2 disjoint families of n minus r sets. The total number of points is more the total size of that level. That's conjecture. That's it. So it's a very nice proof. Somehow, that kind of shows, I said yesterday, that the KK exerts its evil hand, so it's wonderful hand, over lots of other things. Right? This didn't mention shadow at all in the statement, but understanding KK easily tells us what's going on. So I guess the clever idea in that is this this bracket's trivial but very clever first line here. Once you said this and said this, then you're locked into this, and then you remember your KK, and you think, oh, the calculator was nice or not, and they were gorgeously nice, it was a very nice thing to that. Okay, so in that sense, that's the clever line you can get this from trivial line. Okay, that's proof 1. Another proof is also very nice, that doesn't use KK at all, just totally direct. So that proof at least is, you could maybe say, can we do anything to relate to containment and the confidence? The proof I'll show you now is, say, short, doesn't involve KK, but you think, fine, beautiful proof, haven't I think of it in a million years. But on the example sheet today, there'll be one question which I think hints at some motivation for this second proof. Yeah. Are you asking a question? Yes. Right, because an intersecting family means if you take something in the family and take something else in the family's complement, this is not contained in that. And therefore, if you keep adding elements to this, one by one, you never end up in a Y complement. It's not contained in it. But that's right. That makes sense? Okay. So here's the second proof, proof 2. So we're going to think of 1 up to n arranged as cyclic order. So think of a circle, you have the numbers 1 up to n. Please write that in any order you like. Okay? So any order of 1 up to n. 1, 3, 7, 90. I promised I'd never example with more than 9. Sorry, so 9, 8. Okay? Think of those around the circle. That's called a cyclic order. So I guess there are n factorial of those because you just put the elements down. Okay. I want to ask the question, in my family A, how many of its R sets are intervals? Interval means a consecutive block of things, like, for example, let me rub up this in the way. So, for example, that is an interval. Does that make sense? So an interval means a consecutive block of R numbers. So I fix one cyclic order, just fix one at the moment. And then it contains, I guess, n intervals, right? You start anywhere. They can't all be in the fabric, right? Because the interval, this one to this one, and this one right here are disjoints. They can't be in the family. So how many intervals can be in my family? if you took this interval and then you shifted it along a bit, and along again, and so on, you could fit in R, couldn't you? But not R plus 1. Okay. That requires a moment's proof. If R is less than a third n, that's a rigorous proof. But if R is close to half n, it could be that I took a thing here in here and they met round the back. So the formal proof would be to say, the reason you can't have more than R, the formal proof would be to say, fix your one interval you have, and now at any cutting point, you can't have both the thing that ends there and starts there. That means that you can't have both these orange things. So every interval must start or end in that, for sure. You can't have the start and the end, so it gives you R minus 1 new things. Right, one for each division point. So that's your rigorous proof of that. And the proof, the quote obvious proof, only works past less than half n, but this is correct, right? Because this and this really can't be round back. Okay, good. Answer. The most R of them. Good. Now, conversely, if I give you an R set, in how many cyclic orders of an interval? So conversely, an R set is an interval in how many cyclic orders? Let's think about it. I guess you could first decide where the interval is, that's n choices. Then you could order the R points inside it. And then order the big bad rest of the world outside it. So symbols up kind of double count. So let me count, officially I'm counting the pairs, a set in A, an order its interval. So the number of pairs in X in A, comma, an order in which X is an interval. What do we know about the number of these pairs? On the one hand, we know that for each interval, for each order in first R, right? So it's definitely at most n factorial times R, right? Like counting from the right. And so order equals R. And at the same time, it literally equals, you pick an R set in A, that's mod anyways, and then you know it's exactly that number there. N R factorial n minus R factorial. So this unknown number, on the one hand, equals this, and it's at most that. Conclusion, that's at most that. Make sense? This one. No, there's a cyclic ordering one. Yeah, I didn't say the regard to is the same if ... Literally just a bijection with the circle. Okay, so the conclusion, the size of A is at most this over that, right? So n factorial times R over n R factorial n minus R factorial. And if you think about it a bit, I've got on top an n minus 1 factorial. Okay, good. On the bottom, I have an R minus 1 and n minus R, which is also n minus 1 in paper R. So that's n minus 1. Choose your answers. And you'd be allowed to say to me, why is there like this ugly mess here? So when I've written it, I wanted to keep it simple, but it looked like it was likely to work out. But it had to work out because in the extremal case, in the family of all R sets with a 1, you agree in every ordering there are exactly R intervals, not less than R. If I give you an ordering, how is it a 1 exactly R? So a better way of saying this bit we said, this answer must work because in the extreme world case, I have an equality sign there. So it had to work, not lucky work. Okay, so very nice proof. As I say, left thinking, that's beautiful, how do you think of it? In general terms, sorry, this is absolutely not motivating you, to say something about it. In a sense, you could say, we had here a box, this was A, this was the thing we want to count. Thing we want to count. So it happened to be the family A. Here are all the X's there. And the way we counted it, in fact, we said, let's invent, amazing over here, a big box of auxiliary objects. Which happen to be cyclic orders. So here there was a one order, here is another order. Then we said, let's make it a bipartite graph. We said, let's join a line if some condition happens. Because the condition happens to be the beast on the left is integral with the beast on the right. But something. And then we said, let's start to count the edges. We said, number of edges is, at most, number of points on the right times their degree, which is at most vector above, and it equals number of the left times their degree, which is that thing. So this is sometimes called averaging, because basically you're averaging against some constant object. It's also called Katona's method, because Katona invented it. I did tell you that Katona's name quite a lot in the series of talks. And if someone says to you, apply Katona's method, that's never proved at all, because how do you think there's going to be objects? Right? In that proof, the genius is to think there's going to be objects. Right? When we first read the statement of Erdos-Ko-Rado, you think, oh yes, that's cyclic orders. So it's a fantastic, when it works, it's wonderful. You feel warm in your tummy, but people want to improve. It's very hard to think of those things. I said that there's one question on the example sheet, which is about the case where R divides A. If you can solve it, you might use some motivation of how you might motivate this. Very nice thing. Okay, so that's you came up two very nice proofs. Good. So we've dealt with intersecting families in the entire pass. I don't have trivial on one side. We've dealt with it in a layer. That was very non-trivial. That was very good. We can also ask, this was about just intersecting in at least one point. What if you said, I want to be t-intersecting, meaning H is t? What happens then? It's a natural next question to ask. So A in the power set of X is called t-intersecting if the size of X intersect Y is at least t for X and Y. Right, let's think about that one. Very naturally fast. What happens there for, so the whole cube must have been. So the initial number of R sets, just the analog one trivial thing from before. What do we do? So for example, so forget how much can it be? Well, t equals 1 we know all about. Let's try t equals 2. What would be a natural thing to try? Well, since before the winner was, rather trivially, all sets contain 1, have all sets in 1 and 2. So a good guess. We could take the set of all x in the power set such that 1 and 2 belong to x. How big is that? That's got size, or that's a quarter of all sets, right? I'll write size a quarter. Of course, I mean a quarter up or 2 to the n. Okay, sounds good. But do you remember that I said there were other examples? I said that if x is size ends odd, you have the upper half. So here, suppose it's even. Suppose I'm looking at, say, some subsets of 1 up to 8. which are 2 intersecting, you could take all sets of size at least 5, couldn't you? Do you agree to meeting these 2 points because 5 plus 5 is something? So suppose n even, so brackets n even, you can also take x brackets at least n over 2 plus 1. Right, all sets of size at least the middle plus 1, any 2 of those, because their sizes add up to n plus 2, give these 2 points. How big is that? That's basically half 1, isn't it? If you think you're cube. Remember, the levels go up, they're biggest in the middle and go down again. And the middle level has size, well, not the whole lot, it's got size about 2 to the root n, if you want to know that. But it's not anything, right? It's not sort of the whole thing. So if I take this upper half here, that's essentially a half of 2 to the n. So this time there wasn't inequality. The 2 examples are very different. This one was rubbish, this was pizza. And if n's odd, you also like, if n's odd, I could take all sets of size, I don't know, half n plus 7. That means anything lots of, way more than 2. That's also got half more sets. So this is a winning kind of thing. And that's what we'd like to prove now. So we're now going to prove that the t-intersecting, the best you can do is all sets of on a certain level. Of course, there's some little parity condition. I'll do the easy case when n plus t is an even number. So I could just say, take all sets of size at least n plus t over 2. There'll be a similar theorem for all, but you don't really care about that. So here's our theorem. So we have Katona again. This is called Katona's t-intersecting theorem. It says what I just said. It says that A contained in entire set of X be t-intersecting, where the numbers work out nicely, where n plus t is even. Then, the size of A is at most, that's the exact winner, X at least n plus t over 2. Notice n plus t over 2 is a whole number, so leave the thing to write down. Given 2 sets of size n plus t over 2, the size of n plus t is the unity t points. This is what we want to do. As always, it's very nice, it's the exact results. And most terms we're doing here in this course are exact results. Not just saying this is roughly the winner, we're saying exactly the winner. Okay, so how are we going to prove this? Again, the same mumbling as before in KR, we're scared, don't know how to start, and so on. Of course, this time you can't just say, oh, we're related to a shadows thing, because we're not living in level. So there's no such thing like that. But still, let me try and massage it a bit and see if it can relate to something we know about. I want to, again, somehow rephrase the statement t-intersecting, not as things about, this containing that conflict or not. It's very simple. So let's see if we can rephrase it a bit. So what does it mean to say that x intersect y is at least t? Let me draw a cube. I guess I could. Here's Qn. But I want to, inspired by proof 1 in KR, I want to say something, anything about x versus y complement. So you could ask, how far apart in the cube are x and y complement? This is again an example of why, even though the problem mentions only sets and not the graph structure, the graphs we can have. So the distance in the cube, of course, the number point you have to check, right? Like 1, 3, to 1, 4, 5, you've got to kill the 3, add the 4, add the 5, get 3.5, right? In the graph. So if I tell you that x has t places that agrees with y, you've got to kill those to get to y complement, right? So certainly the distance from x to y complement is at least t. The distance from x to y complement is at least t. Let me just say that again. So the distance means the length of this path. In a path, we're changing elements in, out, into, out, out, to it, right? So that's how the graph is defined. Now, if I tell you, so to go from x to y complement, I want to change elements like that. I can either add a 3 or root of 4 to get to y complement. But annoyingly, x already has t points that's very y. I got to y complement. I've got to kill those t, right? So you need at least t steps. I can't not more, but at least t steps. Okay. Now, what does that say in terms of something we know? It says, if you start off with set A, and you take its neighbourhood, it's only distance 1, you neighbourhood again, distance 2. This says, if you take the neighbourhood t minus 1 times, you miss the confidence. Right? So, neighbourhood iterated t minus 1 times of A is disjoint from our usual friend A bar, which as before, A bar would be set of confidence. Okay? Aha! And now we manage to relate things to neighbourhoods which we're experts on via Park's theorem. We know exactly, the set is a certain size, how its neighbourhoods go. Remember, it was simplicial visual segments, which said if you're a ball, go for their size. If you want to have your ball, something yucky with lex, but significant ball size, isn't it? Because that's a ball size number. So, let's try it. So, I'll give you our proof now. Suppose the contradiction that the size of A is strictly bigger than the size of X, at least N plus 2, and so also the size of A bar is more than the same thing. Okay, let's get to work with Ahlswede theorem. So we have the size of A being bigger than, I guess, when we stated half, it was in terms of balls at centre of the origin, not centre of the whole space. Let me just reflect. Okay. Do you agree that this size is also like the size, or sets of size, most n minus t of 2? Right? Sets of size 3 are as many as sets of n minus 3 and so on. So if I take all sets of size least n to t of 2 and just complement it, I get literally all sets of size at most n take that number, which is the size of x at most n minus t of 2. Okay. Now I'm not going to use the strict inequality because I don't understand about strict stuff in Harper. What we'll say is that implies. So think about it. A is at least that ball of that radius. Therefore, take neighbourhood by Harper, it's at least 1 bigger. Right? I'll apply Harper again, at least 1 bigger, and so on. It's always by the nice T case of Harper, but don't fiddle about the lex in the middle. So, by Harper, the size of a neighbourhood iterated t minus 1 times is at least as big as, I'm not going to say no, forget about strict inequality and so on, is at least as big as that neighbourhood of the ball of the same size, which is x. Let's see, I've got to add t minus 1 to that number, which I think is something like n plus t over 2 minus 1. Fair enough? So, what do we have? Here is Qn, of size, of course, the world, to here. I have this red thing, neighborhood t minus 1 of A, which is size this much, and I have my orange thing, a bar, which is bigger than that thing. But that's a contradiction, right? Because those two add up to the whole world, don't they? If you take all sets which have size strictly less than n plus t over 2, and you chuck in all sets of size at least n plus t over 2, that is all sets. So prediction, so on. This is again a nice proof. And again, it wasn't luck that we happened to have a minus sign to be safe. This had to work out because in the extremal family, Katona's theorem, that is an exact thing for the Hawkes theorem, right? So it basically had to work out. So yeah, this shows again how Harper also kind of controls what's going on in different model sets. There's a curious thing actually. So Katona's initial proof was very long complicated with this, and it appeared in Journal of Combinatorial Theory, Volume 1, Issue 1, back in the 1960s. That's the exact same issue where Harper's theorem appeared. But no one noticed for more than 10 years that the 1 implied the other one straight away. So it's quite bad news. So that's kind of good thing. Great, okay. Note that was a lot harder than the trivial thing with the beam state, which was just intersecting all sets. Okay? So what's left to complete the picture, this little diamond, the intersecting for all sets, trivial, level, then t-intersecting for all sets, not trivial, and it was easy given the awesome power Harper, but it wasn't trivial for both principles. Let's complete the picture now by looking at t-intersecting families of our sets. So what about t-intersecting A living in X? So, and again, let's assume things aren't stupid. So let's assume it's not the case that any two R sets trivially meet in at least t points. So let me assume that, say, 2R is less than n plus 2. Whatever you want. Just some condition that says, I think that's actually correct. But yeah, I think we can. Okay, wonderful, yes. If 2R is at least that, then 2R is at least t, so I'm going to take the whole world of all sets. That's silly. So let's assume that for evermore. Okay, so what do we do? Again, there's an obvious example. Everything that contains 1 up to t. Now, is that going to be best? You might say, but wait a second. A moment ago, we noticed that, say, 2 intersecting, everything with 1 and 2 wasn't best, 10 being big is best. But then again, here you can't change the size, right? You don't have the luxury of changing the size. So you can't say, oh, we'll just copy that thing and I'll do the bigger thing. It's actually not what else to do. Let's think about it. You could have a family, which I'll call, say, a 0. That would be all the x in xr, such that square brackets t lives inside x. That's certainly t-intersecting. Or you could do the thing we did before, where you say, actually, let me take t plus 2 points and move t plus 1. So A1 would be the set of x in xr, such that x intersects square brackets t plus 2 is at least t plus 1. Right, that's also t-intersecting. Or you could take the family out to A2. You could at least t plus 2, t plus 4, and so on. Those are all t-intersecting. And they're probably not going to win, given what we do with EKR. It's not, we want to at least look at them. So x intersect t plus 4 So t plus 2. And so on, and until you start picking more pathways per set. Right. Okay, let's try it saying with, well, we know about one, let's do 2 intersecting and say 4 sets from A. I mean, the first, not everything meets in. So let's try and see what happens. Okay. So let's try t equals 2 in square brackets 8 brackets 4. Let's do the round and see what happens. We expect A not to win, but let's see what happens. Okay, how big is A naught? So that's all 4 sets that contain 1 and 2, right? So I believe that is 6 choose 2, picking 2 from the outside. Which is 50, 605 over 2. How about A1? So what's A1? The rules are now not you have the first 2, but you have at least 3 of the first 4. Making sense? That is 2 sets, right? If I have 2 sets, which each have these 3 of those 4, then they would be 2 4. How big is that? I guess there are 2 cases. You could have all 4 of those, or you can have 3. If you have 1 of them, that's 1. And then if you have exactly 3 of them, I guess there are 4 choose 3 ways to choose it. Choose 3 set, and then I'm going to pick on one point out here, and then 4 choose 1 ways to do that. That's 17, which is more than 15. So it's not true that A is the winner. Let's try A2. Now that is everything that meets the first 6 points in at least 4. I.e. it's all 4 sets marked 6. Makes sense? If I pick 4 from the first 6, I have nothing else to pick. So that would be 6 choose 4, which was the same 6 choose 2, which is 15. That's very interesting. So it wasn't true that you know. What would happen if I increased the 8? 8 went to 9 and then, it can't go to 10, that's a 2-digit number, it makes 10. So I'll put 8, I'll put dot, dot, dot. Okay, what would happen if you increase the number? How many 4 sets from 9 are there? At least 4 in the first 6. That wouldn't change, would it? Right, this is all 15. Because you always say, whatever n is, if you want some 4 set, at least 4 in the first 6, it is 4 in the first 6. This one should always 15. Stays at 15. How does A1 change? It's always 1 plus, you pick 3 from the 4, choose 3, and then you pick 1 of the remaining points. So this will go linear, wouldn't it then? Makes sense? It would have been 1 plus 4 times n minus 4. This one, linearly. And how about this one? Well, that's only repeated 1 and 2, so it's always the remainder choose 2, which is quadratic, right? So if you keep going, A will win eventually. It might be a loser at the small end, when it's big to win. That doesn't prove the biggest, but it proves amongst the A alphas. And the ones that are going to do it. Does that make sense? I've not proved that if n is big, the biggest 2-set family of 4 sets is A naught. I've only shown amongst our guesses A naught's the winner. In fact, it is the winner, always, and that's often called the second Erdos-Ko-Rado theorem. That's the last thing we do today. So theorem is normally called the second Erdos-Ko-Rado theorem. It says, given a fixed T and R, if n sufficiently large, then the greatest and biggest t-intersecting A living inside X brackets are beta 0. And you can't beat any 0. It's a very satisfying, nice thing, right? It's like BKR, except you have to say NB. I don't really care what NB that means. I'll do the proof. If you're desperate to, which I urge you not to be, you can check through it. You'll find there'll be some function involving T and R. We'll go at it. We'll go at something that exists. Okay, how do you prove this? So there's exactly one idea. In other words, the idea is going to be the following. This is not going to be clear. Why did this swing? Because you have 2 degrees of freedom, right? But having said, you must have 2 of the first 2, you have 2 degrees of freedom left, right? Among n minus 2 points, who gets what was marked? That's why you've got quadratic, right? This had 1 degree of freedom. I don't care if it's 1 degree amongst n or n minus 5, 1 degree of freedom. So that's going to be the idea. So the idea is going to be, we have, the idea is going to be, A naught has, I guess it's it's R minus T degrees of freedom, right? Oh, yes.
Wondering about the way you stated it. So it's the greatest t-intersecting.
I mean, no, it just, you can't beat that. It's one of the winners, yeah. I mean, it's the greatest size is the size of that.
But it's not true that all external examples are like these t guys and the amount of window.
Well, that happens also to be true, but I'm not going to prove that. Yeah, yeah. So it is unique, but I'm not going to. So I didn't mean it's the unique winner. I meant it is a winner.
Okay.
So maybe sure you can't beat it, or max size is size of A winners. Okay. Has R minus T degrees of freedom. So let's see how the proof goes. So let's take A. Let's let it be maximal t-intersecting. And you may as well just add in the set, you've got to add many more. Okay. Now the reason that's useful is I want to say that in my unknown family A, I would say, of course, some 2 people exactly t. So right the must have the size of that intersect y equals t. The sum x and y. And why is that true? Suppose, on the contrary, the ludicrous idea that in your biggest possible t-intersecting family, order the sector is t plus 1. Right? Take any set in your family and change it one element. Okay? Remove 5 out of 6. That would also be everything in at least t points, right? So you have to add the family. So that would imply that for everything in the family, change one element from the family. That's nullity. That's the whole level, right? Start with any R set, you get any R other particular one in this family. If you have the whole level, which is contradictions, you don't, because n is real. So this would imply, brackets else, x in A implies x, plus I minus j in A, or I not in X, j in X, which would imply that A is the whole of the whole level, which was it. Make sense? So it's a silly remark that it's not the case that in your biggest possible family, every 2 big meters strictly more than t or focus of state. Okay. Picture time. Here's X. Here's Y. And there are t points, this bit here is size t, right? Now, of course, if A is contained in a family like A naught, we're done. Right? If inside A there are t points which belong to every set of A, trivially done, so there's n must not. So we're not going to assume there is some z in A with z not containing the full of x intersect y. Does that make sense, right? If everything in your family contains x intersect y, then those t points from all your sets would trivially done. Okay, let me draw you a z. Sort of Venn diagram. Okay, and the point is that z doesn't have all of that. Right, so this exists, this is empty. Okay, now, think about any set in your family. How much does it meet this picture? It's got to meet x in at least t, and y at least t, and z in at least t, right? So it can't meet this picture in only t points, can it? Because if it only had t points in this picture, then because of x and y, that could be the entire x intersect y, then it's z integral. So the conclusion is, so for every w in A, w intersect my picture, x, union y, union z, has size at least t plus 1. Does that make sense to everyone? But again, if it met this Venn diagram, any t points, then it's got to be x in t and y must be table intersection. If it contains an intersection, it doesn't meet z in t points, right? Because there is something there. It would z in this direction. It's got to be z in t point. It's got to meet at least t points. So any w in the family must have at least t plus 1 point in this finite picture, and now we're done, because that's two millimeters from outside. We didn't write down the final line. Except for the sorry. Oh. So, how big is the size of that? Let's be incredibly crude. We know that every R set in A must meet that picture in at least t plus 1 points. And therefore have at most R minus t minus 1 points outside it. Now, in that picture, I don't care what it does. I'll just write 2 to the power of 3R. Because this picture has size at most 3R. Okay, quite a lot less, but most of it, I've been very, very crude. And it's some subset in there. Okay, at least t plus 1, okay, some subset. Something is nothing, 2 to 3R. Okay, times. Now, what happens outside? In the outside world, there are, well, at most n points outside, and probably a lot less actually, but I'll just write n. And you're picking from that at most R minus t minus 1. So this is R minus t minus 1 plus R minus t minus 2 plus what's that? That makes sense to everyone? But this, yes. Why not? The multiplier is because to specify a set W, I specify it inside the picture and outside the picture. But if I tell you that on the picture it's got points 1, 4, and 7, that's all. And outside of the points 8, 9, and 17, then you know the set 36 points. So I'm just saying to name an R set, it's the same as naming to the set with X, Y, and Z, and what goes outside it. So it's like saying to name a set, an R set, if I tell you which even numbers it has, or which odd numbers it has, you know the set. So I'm saying that, except even numbers are things outside this, and odd numbers things inside this. Make sense? That's a multiplier. Okay. And this whole bit here is a poly in N of degree R minus t minus 1. And therefore, this is definitely less than n minus t choose R minus t if n is large enough. Because that's a poly of degree R minus t. And so on. Of course, if you were sad, you couldn't work out which n would start to work. It's a horrible mess, you know, coefficients of that, and you know, it's so hard, you know. Okay, that's the second Erdos-Ko-Rado theorem. The last thing I'll say, and definitely not prove, is you might ask, okay, that was n large enough. How about for a given n? If I tell you I want a t-intersecting family of R sets, not that n is a trillion, but n is 10, what should you do? And the very, very famous Frankl conjecture said, one of those systems is always the winner. The Frankl conjecture is that for any RT in n, of course, apart from the range where A is equal to 55, largest T intersecting A living in XR is one of A0, A1, A2, and so on. All those nice values we have. Oh, just by the way, if you want to say which one it is, of course you can work it out. If I tell you N, R, and T, you can work which one's best if you want to. And this was open for about 30 years. It was finally proved in the 90s. It was true by Ahlswede-Khachatrian. So they proved this. It's an amazing piece of work. It would take at least 3 lectures to it, but not really prove it. But it's a very, very impressive piece of work. So this is true. You might ask that since for EKR we have that nice proof of bubbling up by KK, and since also KK being isomorphic being has that impact a layer, and also since the t-intersecting theorem, t-intersecting, we used half, shows how tightly can you pack things in terms of neighbourhood of the cube. You might wonder, is there a similar proof for Ahlswede-Khachatrian? So is there some kind of inequality that says you're given a layer, you've got a collection of offsets, and you're sort of adding up the lower shadow in the neighbourhood? Is there some inequality that would imply that instantly? The answer is there is, but it's an open problem. So that maybe in 20 years' time, people will prove this by saying, here's an aspirational inequality about offsets. Oh, look, this implies that. But all those might be just conjecture. No one have to prove it. Maybe not even true. Okay, so stop there. Examples class starts in exactly 10 minutes.